Radioactivity, as represented by the ball, causes electrons to be ejected from their atom. It's an offensive move based on ionization. Ionization disrupts the structure of atoms of which all living matter is composed. An atom is part of a molecule, and molecules are parts of the cell. The cell is the structural and functional unit of all living matter, a tiny machine with a basic job to do. Cells operating with thousands of other cells of various shapes and performing special chores make up tissues and organs. Organs are departments in a complex factory, the human body, which is engaged in the manufacture of an important product, life. An atom then seems unimportant and infinitesimal, a tiny cog on a small wheel in a miniature machine which, if multiplied millions of times, forms the going concern that is you. But if enough of the cogs are broken through ionizing radiation, the gears grind, the machines falter and stop, the factory shuts down. Each of the 4 kinds of missiles discharged by radioactive substances has its own ballistic behavior. To observe them attacking the body, they must be symbolized far out of proportion, magnified millions of times. Gamma rays are the most penetrating, but the least ionizing. Not so penetrating, but more ionizing, are neutrons, which are not rays, but particles. Neutrons and gamma rays are external dangers, able to shoot into the human body easily. Alpha particles cannot penetrate the skin. Beta particles can cause surface burns if the assault is sufficiently concentrated and sustained. Both are able to gain entry through the eating and breathing of radioactive matter or via breaks in the skin. Once inside, this so-called hot stuff takes up residence in various parts of the body, giving off highly ionizing alpha and beta particles. And how long does this radio rat race go on? The body will succeed in casting off some of this material, but it is a long, slow process. There's no effective method for dislodging the stuff. No known way of neutralizing or destroying it. There is no method of hastening its half-life, which is the time required for 50% of the substance to decay. With some substances, it is a matter of less than a second. But if you had some plutonium inside you, you wouldn't make any plans to celebrate the event. Plutonium's half-life is 24,000 years. The various kinds of cells which make up the parts of the body differ in their vulnerability to radiations. Most sensitive are lymph cells, such as those found in the tonsils. Next is bone marrow, which manufactures red and white blood cells. Then the sex cells, followed by tendons and cartilage, as in the nose, muscles, and nerves, the toughest of all. In general, cells which reproduce rapidly and whose efficient functioning depends on that ability are most affected. Radiation halts their reproduction, which is a simple process of one cell dividing into 2. This destructiveness has been harnessed and put to work in the radium treatment of cancer, which consists of cells that have gone wild and multiplied too fast. The manifestations of radiation in the body are many and range from slight to severe. Loss of hair, nausea, bleeding, inability of the body to resist other ailments and make its own repairs. These are some of them, and they may be climaxed by the ultimate symptom, death itself. However, complete recovery is more probable. The illness runs a course from causes to effects. Much of the mystery surrounding it is maintained by the general public, which is determined to regard radioactivity as potent and irresistible as the evil spirits of the Indians. This can be partly explained by man's fear of dangers he cannot sense, a fear fanned into widespread misunderstanding and by sensational speculation on what radiations can do. Radioactivity is dangerous, but to say that it's deadly, period, is as misleading as giving a flat answer to the question, how high is up? The radium-treated dial of your watch, for instance, is harmless. Nuclear emanations became a threat when man isolated such hot stuff as radium and worked intimately with it, broadening its scientific, medical, and industrial use. A threat, however, that has been effectively controlled through observing caution. Not even the atomic bomb burst, man's boldest venture in releasing atomic power, is the DDT of humanity from which there is no escape. For it has its known limits, calling for preventive measures as clear-cut as those doctors lay down in telling people how to ward off infectious diseases. The first and obvious one is, be someplace else when it happens. Distance lends considerable enchantment to an A-burst. But under some conditions, that's a hard rule to follow. Atomic warfare, for instance, might allow little choice in the matter. So if you can't stay away from it, you must stay with it, as safely as possible and properly protected. Proper protection is based on what we know about the penetration of gamma rays and neutrons. The ability of a shielding material to stop them is expressed in half-thickness, the thickness necessary to reduce the radiation's intensity 1/2. In dealing with gamma rays, the half-thickness of a very dense material like steel is 1 inch. That of concrete, less dense, is 3 inches, while 12 inches of wood, which is quite porous, is required. Against neutrons, the density of a material is not so important as its ability to slow down and capture the particles. Concrete, earth, and water furnish good shielding. The best shelters, then, against the gamma and neutron bombardment released by an atomic explosion are strong, reinforced structures. That prompt bombardment of a high aerial burst is severe but short-lived, since it is carried up into the stratosphere. It's safe to go into the area under the explosion about 2 minutes after it occurs. Not so with an underwater blast, however, and presumably in the event of underground and surface explosions. The area is contaminated with radioactive material which gives off alpha and beta particles and gamma rays. However, the material which emits alpha and beta must be taken into the body through the mouth and nose, or skin breaks, before they can carry on with their injurious ionizing. Steps to prevent the perpetration of these inside jobs include eating only food which has been inspected and passed on, guarding against breathing radioactive dust, care in handling contaminated articles such as clothing, washing them or disposing of them if badly contaminated, thorough cleaning, especially the hair and under the nails. Sound medical practice demands not only a knowledge of the way harmful agents operate, but an accurate estimate of those agents. Radioactivity is detected by various instruments, such as this Geiger counter and pocket chamber. They have as their unit of measurement the Röntgen, or fractions thereof. This dial is graduated in Röntgens, allowing for precise readings of contamination in persons and things. It will tell how much radiation the wearer has received. The human body's resistance to destructive agents and its recouping powers vary with individuals. This man might recover quickly from a rattlesnake bite. This one might succumb to a bee sting. Aware of this range of vulnerability, doctors have set extremely safe and low exposures such as 3/10 of a Roentgen per week, as the maximum gamma radiation dose for laboratory and industrial workers with radioactive materials. They calculate that 300 to 500 times this much, 150 or more Roentgens, may bring out symptoms of sickness. The median lethal dose, which is the amount necessary to kill half the persons exposed, is placed by most medical authorities at around 450 Roentgens, received by the victim's entire body and within a short period of time. Thus, it takes a very special combination of circumstances to cause the death of a person by radiation. A combination that's a remote possibility in ordinary work with radioactive materials, and not nearly so frequent in atomic warfare as is commonly believed. But suppose that despite preparedness and preventive measures, one gets a dose sufficient to cause sickness. What then? Is this the stock answer? The unavoidable sequel? Or this? Most emphatically, it's this. Radiation illness lends itself to treatment. The treatment is symptomatic, which means the doctors relieve the symptoms or effects rather than remove the cause. To clarify, when you take aspirin to get rid of a headache, that's the symptomatic approach. Removal of an injured or infected member of the body is specific treatment. A radiation patient is bolstered in all possible ways. The body, a remarkable self-repairing machine, if given half a chance, is assisted in overcoming the effects of ionization. For example, if the patient's supply of red blood cells is down, he is given a transfusion of whole blood. If the count of white blood cells, the policemen, the anti-germ guards of the human system, is so low he can't resist infection, he gets penicillin. Medical researchers are constantly seeking to supplement symptomatic with specific therapy. The atomic bombing of Hiroshima and Nagasaki took the Japanese completely by surprise. Their medical facilities were pretty well knocked out. Nevertheless, an impressive share of radiation patients recovered, and it's estimated that good medical care might have reduced fatalities considerably. The Japanese didn't have that kind of care, yet the deaths attributed to the bomb's radioactivity made up a small part of the total, about 15%. It is reasonably assumed, though, that many who were killed by the bomb's other destructive forces sustained radiation doses that would ultimately have proved fatal. In short, they were burned and beaten into oblivion before they had a chance to die from radiation, which puts the finger squarely upon one of the major fallacies in the public attitude toward atomic weapons. It's the fallacy of devoting 85% of one's worrying capacity to an agent that constitutes only about 15% of an atomic bomb's destroying potential. And that's unsound. Doesn't fit. If you must worry, concentrate on the blast effect of an A-bomb. It's prompt and devastating. It causes a gigantic rearrangement of things, a complete change of scenery, and means sudden death to those who chance to be in the way when it's happening. Don't forget the fires that follow. Consider the flash heat, which changes the complexion of all that it strikes. Bear in mind always that blast and heat are an A-bomb's most powerful weapons, that their lethal range is greater and their effects much quicker than the radiation. Blast and heat are hazards that warrant concern but not panic, because they aren't new or novel. They're the same forces of World War II's conventional bombings, which some of you may have experienced, and you did all right. You're here. As food for thought, the possibility of atomic warfare and its relation to your well-being is understandably on your mental diet. But in your thinking, adopt the realistic viewpoint of a man engaged in a gun battle. His chief fear is not that he might come down with a case of lead poisoning, but that he's apt to get an extra hole in his head. Some of the falsehoods circulated about radiation effects are trivial, but upsetting. They're beamed right at one's self-esteem. And
will eventually result in a race of bald-headed people. Just imagine it. Imagine yourself with no hair. They'll call you old skinhead, old chrome dome. And that's not all radioactivity will do. It will...
Enough exposure to radiation will cause loss of hair. The treatment, if you'd insist, would be symptomatic, a toupee. But the condition would only be temporary. Your hair would come back, same color, same cowlick. A fear that is grossly built up in popular print is that radiation will cause impotence, which is the mechanical inability of a man to fulfill his sexual role. That fear won't stand examination. Another subject of misgivings is sterility. A sterile man can carry out his sexual obligations physically, but is unable to fertilize, to reproduce his kind. The estimated dose needed to bring about permanent sterility exceeds the lethal dose. So obviously sterility by radiation would be just incidental, a matter a dead man wouldn't worry about. The public has been force-fed grave suspicions that extensive use of atomic energy, as in war, might eventually result in an overabundance of freaks, suitable for sideshow exhibition. We can start picking the freak possibilities apart by looking at a sperm cell, the kind of cell that plays a leading part in reproduction. These chromosomes contain the material through which such physical characteristics as color of hair and eyes are handed down from parent to offspring. Sometimes the chromosomes are broken up. This upsets the heredity controlling material when the cell divides, and the result may be a mutation, a variation from the parent. It occurs naturally and may also be brought about by radiation. But radiations can't produce any new kinds of mutations. They can only increase the natural rate. Is the increase enough to stew about? No. We can't experiment along these lines with humans, but we can observe the effect of radioactivity on mice and fruit flies, which produce new generations so frequently that to study them for a short time is like reviewing a long span of mankind's history. These are the probabilities, and they aren't important enough to lose any sleep over. Besides, a mutation can be a good variation, an improvement over the barren. If you'll be honest with yourself, face the facts, you'll probably realize that your principal worry ought to be that your offspring will look just like you.